With that being said, our first presenter is David Kring. David, are you online?
This is Houston.
Hi. Take it away. It's all yours.
Okay, so for the audience, I have more slides than I can cover in 5 minutes, provided them in case these do go online, so you'll have a complete story. If I could have the next slide. Okay, so the first thing I want to point out is here's an array of a lot of big ideas that came out of the Apollo program, up to and including the discovery of low amounts of water in lunar samples, which has led us to start thinking about ISRU opportunities. All of these big ideas emerged from sample return, which just goes to illustrate how powerful that type of science is. Next slide. Okay, so as we go forward, we go into the South Pole region, which is an impact terrain. You're going to ask, what type Next slide. Okay, let's go on to the next slide. Okay, so we actually have some data. I'm not going to go through this table, but this is the Apollo and Luna program data. So we have real data. So this is a question that we can answer rather unambiguously. Next slide. We can plot up the sample masses returned to Earth as a function of EVA time, which includes instrument deployment time for each of these missions. Next slide. As you know, 11 was a G mission, land and return, and then 15, 16, and 17 were J missions were far more complex, both in the science that they were doing as well as the terrain that they were exploring. Next slide. Well, you can actually plot this as mass return per EVA time in hours, which I've done here. Next slide. And you can, with the exception of Apollo 11, get a very nice average value of 2.3 kilograms per EVA hour per crew member. We can now use that to anticipate what Artemis 3, 4, 5, 6, and 7 missions might generate. Next slide. So, if we apply the NASA Human Operations published September 24th, 2019, which includes a 6.5-day surface mission and 24 hours of EVA, we can use that pre-existing data to calculate that there should be 110 kilograms of sample mass collected by those astronauts. Go to the abstract if you want more details. Next. Now, the other way of getting at that number is actually to design a traverse, identify sample locations as you see here. Next slide. And then use CAPTEM recommendations for each type of sample type to sum the mass of samples that one would be collecting. So, for example, a brecciated sample of impact ejecta on Shackleton, the recommendation is 5 kilograms per sample. Next slide. Okay, so that then brings me to some summary findings. Based on data from 6 human missions to the lunar surface, an average of 2.3 kilograms per EVA hour per crew member can be anticipated. In the specific case of the Apollo 16 mission to a highlands terrain similar to that at the South Pole, the value was just slightly higher than 2.3. This method to derive estimates of EVA sample mass was incorporated into a recommendation by NASA's Curation and Analysis Planning Team for Extraterrestrial Materials, that is CAPTEM.
That's 1 minute.
Well-trained crew. Thank you. Well-trained crew will only collect those samples needed to address the mission's science and exploration objectives, and that has an important corollary that's constantly overlooked. Samples are high-graded when collected, and any further high grading will only diminish the mission's ability to meet its science and exploration objectives. For polar landing sites, a well-trained crew collecting appropriate geologic samples must have extensive training in that type of terrain. Next slide. Okay, so the last couple of slides actually walk you through the details that were requested for these types of presentations. So for those of you who need information about potential mass of the investigation, potential costs, and so on and so forth. You will find that in these last couple of slides. Thank you.